When we look at Arakoth, we're essentially looking back in time, at an untouched remnant of the solar system's earliest days. The conditions under which this peculiar two-lobed object formed offer clues that challenge and refine our understanding of how planets came to be. To start, scientists estimate that the two lobes of Arakoth, known as Ultima and Thule, merged at a speed slower than 2 meters per second. That's slower than walking pace. Such a low-speed collision suggests that these bodies were in a gentle gravitational dance before they slowly merged. For this to happen, it's also likely that the two were tidally locked to one another prior to contact, showing each other the same face over and over again for millions of years. The fact that both lobes look so similar in shape and coloration further supports the idea that they formed in the same region of the early solar nebula. They likely coalesced from the same clump of material, meaning Arakoth isn't just a random pairing of two objects, but a natural, slow-born binary that became one. Before Arakoth received its official name from the International Astronomical Union, it was informally called Ultima Thule, a term used historically to describe lands beyond the known world. Though poetic, the name was replaced to reflect cultural sensitivity and honor the indigenous Powhatan Algonquian word Arakoth, meaning sky. The images from New Horizons revealed several bright regions on Arakoth's surface, especially around the neck where the two lobes are joined. Scientists believe these areas could be composed of different ices or finer particles that settled into gravitational low points over billions of years. The neck region may have acted as a natural collection zone for such materials, creating a distinct, reflective band. There's also the matter of Arakoth's rotation. It turns once every 15.9 hours, a relatively slow spin for such a small body. Combined with its flattened, pancake-like shapes, this slow rotation suggests that Arakoth didn't undergo significant disruption or heating after it formed. No large impacts, no tidal stress, no resurfacing from internal forces. It is, in every sense, a cosmic fossil. And this fossil preserves a narrative that stretches back over 4 billion years. From a scientific standpoint, Arakoth validates the cloud collapse model of planetesimal formation. This theory proposes that instead of small objects bumping into each other over eons and gradually growing, bodies like Arakoth formed directly from a rapid collapse of pebbles and dust in a dense region of the solar nebula. In just thousands of years, astronomically instant, they became whole. This kind of formation explains why Arakoth's two lobes are so well matched in composition and appearance. It also supports the theory that larger planetary cores could have formed quickly, perhaps solving long-standing mysteries about how gas giants like Jupiter grew rapidly before the solar nebula dispersed. But Arakoth doesn't just teach us about ancient physics. It serves as a reality check. In our pursuit of interstellar discovery, we often focus on big targets, planets, moons, exoplanets. Yet this tiny YIM object billions of kilometers from the Sun reminds us that the smallest things may carry the oldest truths. Arakoth has no atmosphere, no heat, no magnetic field, but it has a story preserved in ice and rock, uninterrupted for billions of years. This is where missions like New Horizons shine brightest. They're not just about dramatic flybys or pretty pictures. They're about peeling back the layers of time, molecule by molecule, light curve by light curve to understand how everything began. Think about what had to go right. A spacecraft launched in 2006, timed to meet a moving object discovered 8 years later, programmed years in advance to execute maneuvers autonomously, all to capture images of something no one had ever seen clearly before. And it succeeded. New Horizons' success with Arakoth demonstrates not just our technical abilities, but our patience, our willingness to commit to a journey that would take over a decade to bear fruit. It's a reflection of humanity's enduring curiosity. As we continue to analyze the data sent back by the spacecraft, scientists around the world are refining models of early solar system dynamics. They're revisiting theories of accretion, atmospheric development, and orbital evolution, all sparked by this little object that floats in the darkness, untouched and unassuming. And New Horizons? It's still moving, still alive, still listening. Now more than 50 astronomical units from the Sun, the spacecraft has entered the realm of interstellar exploration. It continues to collect data on the solar wind, cosmic dust, and the structure of the heliosphere, the invisible bubble that surrounds and shields our solar system from galactic radiation. These observations, while less flashy than planet flybys, are crucial. They help us understand where the Sun's influence ends and where the Milky Way begins. Just like Voyager 1 and Voyager 2, New Horizons is becoming a scientific ambassador to the stars. But what lies ahead? That depends on what it finds. New Horizons has the fuel and power to operate through the late 2020s or early 2030s. If a new target is discovered in time, it could attempt another flyby, perhaps of an even more primitive Kuiper Belt object. Even if that doesn't happen, its ongoing measurements will continue to shape our knowledge of the solar system's edge. So, what has Arakoth truly shown us? That the story of creation isn't just explosive and violent, it can also be quiet, graceful, and ancient. That the universe doesn't always build with fire. Sometimes it assembles with stillness, with cold, with gentleness, and sometimes that's enough to change everything we thought we knew. Join us in the next segment as we follow New Horizons further into the unknown, charting a path through interstellar space, guided only by the faint signals of a spacecraft that refuses to stop exploring. Only here, on Infinity Beyond.